Hello my friend, welcome to another video. Today we keep our discussion on threads, and especially we're going to talk about deadlocks. So first thing first, we're going to search for the actual definition of deadlock. On Wikipedia we find this. Deadlock is any situation in which no member of some group of entities can proceed because each waits for another member, including itself, to take action, such as sending a message or more commonly releasing a lock. Confusing. In an operating system, a deadlock occurs when a process or thread enters a waiting state because a requested system resource is held by another waiting process, which in turn is waiting for another resource held by another waiting process. All the times when I read these technical definitions, I think to myself, what the, what? All right, so here we have a little scheme that explains a deadlock. Basically, we have this circular waiting, right? We have all the processes that are waiting a resource taken by another process. So we have everyone is waiting for the other process. This is too abstract, so I want to give you a very silly example coming from real life. So the first thing I thought when I stumbled upon this concept of deadlock is this. A Mexican standoff, right? In which we have all the cowboys that are stuck waiting the move of the other cowboy, right? So with this very simple, silly example, I would like to explain the concept of deadlock. Basically, we have two or more threads unable to continue their execution because they're each waiting for the other to release a resource. Every thread is going to be one person, and the actual resource to be released is going to be a gun. So I can model a cowboy with a thread and the resource with the mutex, right? I can do that. And in our example, we are going to have that a deadlock happens when a thread is not able to lock another mutex. So if everyone is able to take his own gun, we have a deadlock. We have a Mexican standoff. On the contrary, if a thread is able to take another gun from another person, we don't have a standoff. We have a kill. I'm going to write a code with only two threads, so it's going to be super simple to understand the overall principle. So we're going to do that. A deadlock is a Mexican standoff to me. I hope this analogy is going to make it simple to understand. So let's write some code. As usual, we include our header files, stdio.h, and of course the pthread.h, POSIX thread. First of all, I want to create my actual struct, right? The struct that is going to represent my thread, my cowboy. So I do struct as cowboy, and inside this struct I'm going to have, of course, a chart star, which is a name, and I'm going to have the actual thread. So pthread type thread. Of course, I'm going to have typedef here to make it simple to use this struct. So I'm going to do typedef, and here at the bottom I'm going to put type cowboy. Easy peasy. Let's go in the main function. So int main. Now here I actually have to create my two cowboys. So I'm going to declare them and initialize with the values. I'm going to use the names coming from the bad, the ugly. So let's do that. Type cowboy. I'm going to do ugly as the name in the film, and I'm going to initialize in this fashion with the name. So string literal ugly. And the second parameter is going to be the actual identifier of the thread, which is going to be provided by the pthread create. So now we don't do anything. I just copy the line like that, and I do the same for the bed, which is the other one, and of course the same name, so bed. All right, so let's create with pthread create. All this stuff comes from the previous video, so I'm gonna go fast. The first is gonna be a pointer to the actual thread. So what do? I say ugly, which is a struct. So dot to access a member variable, thread. Now I accessed the member variable and I need an address of that, okay? Because this is a pointer. I don't need any parentheses because here the precedence is totally correct. If you have any doubt, I made a video about operators precedence. Now the other parameter is going to be a null. We don't need this. Like that. The other parameter, on the contrary, is pretty important, which is the actual pointer to function. And we're going to say action, for example, like that. A pointer to function doesn't actually require the ampersand, as you often will see, because it is only redundant. This is already a pointer to function. Then at the end, I have to pass the actual address to the struct. So I'm going to pass the address to ugly, like that. All right, that's it for the first one. We're going to yank this past and make the same for the bed. Right, this is going to create the actual two threads. Of course, you have to pass bed. Now we have to call the join function for both. So pthread join. First input is going to be the thread value, so ugly thread. And the second one we don't need. So it's going to be null. And we do the same for both threads. Bad, like that. All right, now we just have to implement the actual action. You know that the function coming from the pthread create as this prototype. We have a void star action, so our function that returns a generic pointer, a void pointer. It takes as an input as well a void pointer. So here we say data. Here you see that we pass a struct, a specific struct that has type cowboy data type. So here we simply do that. I declare my cowboy, that I call cowboy. Then I assign to this the actual cowboy given as an input. How do I do that? Well, first of all, I have my generic pointer, which is data, right? The thing is that this is a pointer pointing to a type cowboy struct, right? So I am to tell, hey, you are actually a pointer to that object. So type cowboy pointer. I'm casting this generic void pointer to an actual pointer to a type cowboy. So now I can dereference this pointer, right? So I do that. I dereference this new pointer and I get the object. This void pointer as an input is a common theme in C, right? Because this is allowed to pass almost everything. It's up to the programmer, it's up to us to decide which kind of data is pointed. Like in this case. At the bottom, of course, we have a return null. All right, that's already a blueprint of our project, of our little program. Now, what is the actual action? What we want the cowboys to do? A deadlock happens when we don't have progress, right? Our code is stuck. We're stuck in a situation. For example, if a thread wants to access a specific resource which is locked and is never unlocked. We can say that our resources are guns in our case. So the model is going to be this. The two bandits, the two cowboys, will reach their guns, right? They're going to take them, so they're going to lock, in our case, the mutexes. The other operation is trying to lock the other's gun. This is not possible, right? You see, because both resources, both guns are locked. So here, my friend, we are in a deadlock. We are in a Mexican standoff. Both cowboys are waiting the move of the other, but nobody does anything. Nobody shots. Nothing happens. We are stuck. We are in a dead. Let's implement this in code. So first of all, I have to create my resources, which are going to be mutexes. So let's do that. Guns. I say p thread mutex type. I say gun is equal to, I'm going to use pthread mutex initializer to make it fast. I'm going to do the same with the other mutex, which is bad gun. And we are ready to rumble. So these are going to be the actual resources that are going to create the deadlock. Let's write code. So first of all, I have to understand which cowboy I'm dealing with. So I'm going to include string.h, right? To use the string compare function. And here, what do I do? I say if string compare cowboy dot name is equal to, here I'm going to put a string literal, which is ugly, for example. Here, you know that the string compare function is giving me back 0 if the strings are equal. So here I can say equal to 0, but I actually prefer this way of doing things, like that. I'm going to put a bang, an exclamation point at the very beginning, so I can invert the logic. If the strings are equal, I'm going to invert the 0 in a true Boolean value. So here there is written, if the strings are equal, actually. The bang is crucial here. What do? Well, you're going to lock, you're going to take your own gun, right? So we do that. Pthread mutex lock. I need the address of the actual mutex, which is ugly gun. That's it. Else, it means that you are the other one, because here we have a binary condition. We only have two threads. you are the bed thread. So you're going to do the same. We can copy actually the code and put bed gun. So in our silly animation, we are here. The two cowboys are taking their own guns. Perfect, easy. And what do? We say, I wanna take the other gun. So you say basically the same thing as here, right? I can just copy this code like that. Of course, this is not elegant, but we just want to understand the deadlock thing. And I just word the logic. If I am the ugly thread, I want to take the bad gun. On the contrary, if I have the bad, I want to take the ugly. You see, this is where deadlock will happen, right? First of all, let's put a print here, a printf, and let's say %s as taken on gun. And of course, we have cowboy name. Okay. So this is a minimal code that is showing you a deadlock. This will deadlock exactly here. So GCC deadlock. And as you can see, I have ugly has taken his own gun. Bad has taken his own gun. And then we're stuck. You see the prompt is here, it's waiting. Nothing happens. It's like a infinite while loop, right? So this is a minimum viable deadlock. Why is that? Well, when we talk threads, you have to assume that they run parallelly. This is not always the case because we have the scheduler, we have the fact that we don't have all these cores. If I have 500 threads, they cannot run parallel, right? So we are always talking about concurrency, but in your mind, you have to assume that these lines are running parallelly. So I have the first thread, let's say the ugly thread that is taking his own gun. The other thread is taking his own gun. And then what happens? I have ugly that tries to take bad gun, but it is locked, right? It is locked. As well as the bad cowboy that is trying to take the ugly's gun. You see what happens here? We have the circular waiting. Both cowboys are waiting on each other. Let's go back to Wikipedia. Maybe now it makes more sense. In an operating system, a deadlock occurs when a process or thread enters a waiting state because a requested system resource, in our case the gun, is held by another process, right? Which in turn is waiting for another resource held by another waiting process. In this case, we have only two threads that are waiting on each other. Maybe now the definition makes more sense, right? I hope. Of course, there are more details to this deadlock thing, right? You should read these conditions for deadlock if you want to have better understanding. But the basic idea is this one. We are stuck because we have resources that are locked and threads cannot proceed. So now I want to introduce some randomness to my code. I want to introduce some randomness to understand better this deadlock deal. So in this case, we have that one thread, one cowboy is going to be slower than the other. The result is that one cowboy is going to lock the other cowboy's gun. It's like one cowboy is snatching the guns to the pocket of the other cowboy, like that. You can imagine like that. Then when the slower thread is going to wake up, it's going to be too late, right? It's going to check for the gun, but it is already locked. It cannot take it, you see? On the contrary, the other cowboy has both guns and is going to finish the actual Mexican standoff. He's going to shot the other cowboy, and that's it. I want to write this in code, okay? Let's do it together. To do that, I'm going to need the random function. So we're going to include time.h. Then we're going to include the standard library, and we're ready to rumble. Now, the classic pattern when we have a random call, we have to seed the random function. So I'm going to call seed rand time null. This is the classic pattern. If I want to make it more random, given that I'm going to call this program many times, I can multiply this value by getPid, because getPid every time is going to be a different value. To use getPid, I just need to include unistd. Right? You understand this point. GetPid is the PID of the actual process, which every time is going to be different. Then what do? I'm gonna add inside my struct cowboy a value, let's say unsigned long. This is gonna be reaction time. Basically, how fast my cowboy is. And here I'm gonna initialize in my main reaction time with rand modulo, I don't know, 10,000. 10,000 because I'm gonna use the useLeap function, which works with microseconds. So I think this is a good value. I'm gonna do the same with the other cowboy. All right. Now, before taking the actual gun, locking the actual gun, we have this. How fast the cowboy is. This useLeap. So useLeap cowboy reaction time, right? And I want to know this time, so I'm gonna call a printf and %s reaction time percent long unsigned. Here I just want to make it more clean, so I'm gonna put some emoji, and then I'm gonna use, thanks to our friend ChatGPT, these ANSI escape codes that allows us to make the printf output more clear with colors and stuff. So it's gonna be better. So for this kind of tasks, ChatGPT is really amazing. So I'm just gonna copy some of them, and I'm gonna just put here at the top of the program. There are many ones, but I need few. I'm just gonna make reaction time here bold cyan, the color. Here at the bottom I do reset. Cowboy name. Okay, this is a fancy printf that is telling us information about the time taken by the cowboy to react. So now we have the actual program in its totality, right? We have the actual guns, the struct, and here the action. Every thread is gonna wait a random amount of time, given this microsecond, and this is the actual function. Now, here I should have an exit, okay, like that, if I want to really mimic what is happening in my example, so exit success. But by now, I will just comment this so we can understand better why we need that. Okay, let's launch it. What do we get? We have ugly reaction time is equal to this value, but reaction time is faster. So bad has taken his own gun, and then bad killed the other. But you see, we are still stuck. Why is it the case? Well, the problem is that one thread is still waiting to get his actual gun, but the other thread has already finished, and we are done. Nobody will ever unlock this thread. So what do? Uncomment this, because if we are able to reach this level, it means that one cowboy has been able to kill the other, so we can exit. Here we are stuck because we have this pre-thread join, right? The main thread can never end until one thread is not finished, and one thread is going to be stuck forever to unlock its own gun. So this is the actual action function that is modeling our Mexican standoff. Let's do something now. I'm going to compile, and then I'm going to launch this many times like that. While through, I'm going to launch the process. Let's go there. See, I have many processes that are going to be launched. Let's make the output more clear so we can understand better. So let's launch again, and let's see. You see, we get different reactions time, and the faster, in this case, is going to be the ugly, right? It's going to be able to take his own gun, and he's going to be able to kill because has been able also to take the other's gun. Now let's go down. At a certain point, we have this. As you can see, we have reaction times, which are kind of similar, but nonetheless different in microseconds. So bad has been able to take his own gun, as well as ugly. So we are again in a deadlock situation. You see how random it is. Now you may say, why is that the reaction time are different? Nonetheless, both threads have been able to take the actual gun. First of all, the useLeap function is not totally precise for specific reasons. If you want to dig down a little bit, I wrote an article here in Medium in which I talk about these effects, right? Why the useLeap is not reliable, and I talk about microseconds, why useLeap works in microseconds, and so forth. So if you want to dig down, I leave this in the description. But the take-home message is that underlying that, we have the operating system scheduler that is going to decide when a thread is going to run. So the useLeap approximately tell me, okay, these, as you can see, have very different values. So I'm pretty sure that one thread is going to be faster than the other. But let's launch again. We can launch this code many times and we can check all the values, right? For values that are approximate we have deadlock. For the other ones, no. So this code is not safe, right? For the way it is written, it's not safe. It can run many times, but at a certain point, we stumble upon a deadlock. You see? I want to show you something. If I remove the getPid, so I don't multiply the seed for getPid, so this code is going to be less random. I'm going to launch, and look at that. We have very often the same value, and look carefully here. We have exactly the same values for all of them, right? Ugly reaction time is always 8,985. A bad reaction is 9,800. For all of this, Ugly has been able to take the other's gun and kill. For this case, no. So you understand that underneath the hood, we have the OS operating system that is the real boss. So our sleep here and there are not assuring that we have the actual sequence that we want with threads. So we have to really pay attention. All right, this code is in my Medium article if you want to watch by yourself. And I think that's it for this deadlock. Hopefully it's not that difficult now, but this stuff is tricky. When we work with threads, it's a major pain in that place, you know where. All right, enjoy, my friend. Thank you for watching.